So now we are again continuing with the chapter of atoms and nuclei, and our context of discussion is X-rays. X-rays were first of all practically demonstrated by Röntgen, and he was awarded Nobel Prize for that. Now regarding X-rays, first of all I will brief the conceptual approach of X-rays, that what basically the X-rays are, what are its properties, and how they are produced. Then we will classify X-rays like soft X-rays and hard X-rays, and then we come towards the continuous X-rays and the soft X-rays, that is characteristic X-rays. And from this study only, later on it was found that the basic property of the element is not atomic weight, rather it is atomic number, and this was suggested later on by Moseley. And Moseley suggested that the physical and chemical properties of the elements are the periodic function of their atomic number, not atomic weight. But earlier, Mendeleev suggested that the physical and chemical properties of the elements are the periodic function of their atomic weight. But if we assume this particular statement, then we find that there will be a lot of vacancies in the periodic table and the vacant places cannot be identified. So now regarding X-rays, first of all, we can say they are high frequency photons. So X-rays are photons, their energy is h nu or hc over lambda. Moreover, they have no charge. So they are not deflected by electric or magnetic field. Their speed is the same as that of light. Moreover, X-rays, they produce heat when they interact with solids, the liquids and gases. Another important thing regarding X-rays, that is X-rays produce fluorescence when strike barium platinocyanide and many other complex salts. That is, the property of fluorescence is very dominant in X-rays. One thing must be more clear, which I have earlier explained also, that fluorescence is the property of the radiation. That is, whenever radiation will strike a material, the glow will continue on the fluorescent screen. And when we cut off the radiation, the glow will disappear. But in phosphorescence, we don't find like that. That is, in phosphorescence, when the radiation is falling on the material, the glow is there. And even when we cut off the radiation, the glow continues. It means that in phosphorescent materials, the radiation is first absorbed. And when we cut off the radiation, then we find that it will be emitted out in the form of light. Another thing regarding X-rays, they can ionize solids, the liquids and gases. Moreover, X-rays has a very typical property that is called the coefficient of linear or linear absorption coefficient. Linear absorption coefficient. It is represented by mu. So the linear absorption coefficient, that is mu, is defined as the amount of radiation absorbed per unit thickness of the metal plate. The unit of mu will be 1 over centimeter, 1 over meter, or 1 over kilometer, that is inverse of length. So the dimensions will be m naught, L minus 1, T naught. For linear absorption coefficient, we use a formula I is equal to I naught e to the power minus mu x, where I is the intensity of the radiation emerging out from the plate. I naught is the intensity of the radiation falling on the plate, and I naught minus I will be absorbed by the thickness x of the plate. Mu is supposed to be the linear absorption coefficient. So if you wanted to find the formula of the linear absorption coefficient, it will be 2.303 log, that is I naught over I, or we can take otherwise, divided by thickness. So in X-rays, this is one of the special properties, that is linear absorption coefficient. Another thing is that X-rays is usually not indicating the photoelectric emission because it depends upon at what voltage the X-rays are generated. X-rays can be the soft X-rays or the hard X-rays, whereas soft X-rays are generated at a lower voltage, that is of nearly 100 volts, and hard X-rays are generated at a very high voltage, about 10 to the power 5 volts. So X-rays have a frequency which has an order of about 10 to the power 18 to about 10 to the power 19. However, it is slightly less than 10 to the power 19. But it varies from 1 angstrom unit, that is from 10 to the power 18 to 10 to the power 19. And the wavelength, that varies from 1 angstrom unit to about 0.1 minimum. And 1 angstrom unit is 10 to the power minus 10. In order to produce X-rays, we take a Coolidge X-ray tube in which there is indirectly heated filament and an anode plate. So basically what we do is that we consider a discharge tube or a vacuum tube in which there are two main components. One is that is filament, which is heated with the help of LTB, that is low tension battery. Electrons are emitted. Then we accelerate these electrons towards the anode plate or the target, and we have to apply suitable voltage. So if electron is emitted from filament and it moves at V volts, then energy of electron, that can be taken as EV. So energy of electron is EV when it is accelerated towards the target. Well, target is made up of high atomic weight element, maybe platinum, tungsten or molybdenum. If it is a low atomic weight element, melting point will be less. So we will find that of some time there will be deformation in the target. So to avoid that, we require high atomic weight target, and these are platinum, tungsten, or it can be molybdenum. So when electron energy EV strikes the target atoms get excited, electron jumps from low to higher permitted shell in accordance with the Bohr's atomic model. And when electrons jump from higher to lower permitted shell, we find that electromagnetic radiations in the form of X-rays are generated. And the energy of these X-rays will be h nu or h over lambda. If we assume it's a total transformation, we use the formula EV is equal to h nu or hc over lambda. And from these equations, we get the value of the frequencies and wavelengths. The hard X-rays are used for radiotherapy, that is, for taking the photograph of the internal constitution of the body, or sometimes hard X-rays are used in crystallography. That is, we pass X-rays into a crystal and we apply the Bragg's law, that is n lambda is equal to 2d sine theta, and from that we come to know what will be the approximate separation of the atoms in the 3 dimensions of a crystal. But the soft X-rays, which are produced at low voltage of about 100 volts, we find that the soft X-rays are used for radiography, that is taking the photograph of the internal constitution of the system. But with the help of hard X-rays, we treat certain diseases also, and we study the crystal structure. Now we come towards the main concepts of the X-rays. So all these facts which I have spoken, these will be used in the generation of X-rays and the properties of X-rays. So now we come towards the main concepts. X-rays were first discovered by Wilhelm Röntgen in 1895. They are also sometimes known as the Röntgen rays. The discovery was carried out by Röntgen in Germany. X-rays are produced by bombarding high-speed electrons on the target of high atomic weight and the high melting point. These targets, which I have named just now, are platinum, tungsten, and molybdenum. The wavelength of X-rays lies between gamma rays and ultraviolet rays. Gamma rays has a wavelength of about 10 to the power minus 11 meters, whereas for ultraviolet rays, it is about 10 to the power minus 8 meters. So normally the wavelength of X-rays are found to be about 10 to the power minus 10 meters. The wavelength of X-rays is nearly 0.1 angstrom unit to about 100 angstrom unit. You can recollect that 1 angstrom unit means 10 to the power minus 10 meters or 10 to the power minus 8 centimeters. The frequency range of X-rays is about 10 to the power 16 hertz to about 10 to the power 18 hertz. So this is the frequency range. But if we will speak more elaborately in our experiments, we find that it generally varies from 10 to the power 18 to 10 to the power 19 hertz. 10 to the power 19 hertz stand for hard X-rays and 10 to the power 18 for soft X-rays. Now we come towards, that is, X-rays were discovered by, we will find that frequency range is this much, and the energy range of X-rays is about 100 eV to 10,000 electron volts, or 1 lakh, that is, it should be 10,000 electron volts. Electron volt is the smallest unit of energy, and 1 electron is equivalent to 1.6 10 to the power minus 19 joules, or 1.6 into 10 to the power minus 12 ergs, where 1 joule is 10 to the power 7 ergs. Now, the description is given for hard X-rays. High frequency X-rays are called hard X-rays. As I have just now explained, hard X-rays has the maximum limit of frequency, which is approaching 10 to the power 19 hertz, and the wavelength 10 to the power minus 11 meters. Hard X-rays have high penetration power. The wavelength range of hard X-rays will vary from 0.1 to 10 angstrom units. That is, if the wavelength is small, obviously the momentum will be greater because P is h over lambda, or P is equal to h nu over c. They have a high frequency, 10 to the power 18 hertz. However, the maximum limit is slightly less than 10 to the power 19 hertz. And high energy is about 10,000 electron volts. Soft X-rays, they are called the low frequency X-rays, normally 10 to the power 18 hertz, and they are used for radiography. These have low penetration power as compared to hard X-rays. Therefore, soft X-rays are basically used for radiodiagnosis. They have a higher wavelength, and as I have made it clear earlier also, the wavelength varies from 10 to the power minus 10 to minus 11. So we can convert an angstrom unit also. 1 angstrom unit is 10 to the power minus 10 meters. They have low frequency, and lower frequency is basically from 10 to the power 18 hertz, because maximum it can go up to 10 to the power 19, and energy also less. However, energy of X-ray photon is calculated by using an equation E is equal to h nu or hc over lambda. So from that calculation, it comes to be nearly 100 electron volt or 10 to the power 2 electron volts.